presented by Caltech.
It's a pleasure for me to introduce Greg Fiete, who is now currently on faculty at University of Texas, Austin. So Greg did his PhD at Harvard, working with Bert Halperin, but also with many other people, mostly on mesoscopic problems. And then he moved to KITP, where he did some very nice work developing theory of so-called spin incoherent Luttinger liquids, which is new regime in one-dimensional electronic systems, but also of experimental relevance for quantum wires. And he joined us he became Prize Fellow in 2006, and I should say from the start he was an equal colleague and even helped guiding graduate students at Caltech. And in 2008 he moved to Texas, to Austin, and where he worked on, actually while at Caltech, he worked on very interesting problems in fractional quantum Hall physics, which have to do with direct experimental probes of fractionalization. And when he moved to Austin, he started working on systems with strong spinorbit and strong interaction. So spinorbit is what gives rise to topological insulators, and there is much hope that when combined with strong correlations, one can find even more exotic phases, and I guess this will be subject of his talk today. And I should say that Greg's work has always been closely tied to experiments, to real materials, and helps guide in particular searches for such novel phases in these materials. So.
All right, thank you very much, Olexei. Organizers for inviting me here to this symposium. It's been quite interesting for me. I enjoy hearing some of the latest results from different fields. I'd also like to thank Olexei and Gil Raphael. I don't see him here, but those two were instrumental in my coming here to Caltech as a Prize Fellow, and in fact, I've known them for a long time, since I was a graduate student. I think Olexei was a postdoc at the time, but Gil was also a graduate student at Harvard at the same time that I was. So we've known each other a long time, and it was a great opportunity for me to come here and pursue some independent directions. So in addition to the scientific aspects, which I'll get to in a moment, I do want to make a few personal remarks. Caltech is very near and dear to my heart for a number of reasons. So one of which is that my first child, my daughter, was born when I was a Prize Fellow just down the road at Huntington Hospital. And so coming here to Pasadena this is my first professional visit actually since I left, was quite nostalgic experience for me, coming down, seeing the hospital, seeing the places that I used to push her around in the stroller, and all of those places, even the place where her name got some inspiration, because she was born and we didn't have a name yet, and we needed to take her out of the hospital soon. But I got inspiration for her name here in Pasadena. So besides my daughter's birth, my wife at the same time was a Prize Fellow in biology. She was a Broad Fellow. She's also on the faculty at UT Austin as a computational neuroscientist. She's a physicist by training. So there are two of us that have Caltech affiliations, but our roots actually run much deeper than that. So her brother, my brother-in-law, was a PhD student here at Caltech in condensed matter theory, worked with Peter Weichmann. And his uncle and my wife's uncle was a student of Peter Goldreich. I don't know if he knows that, Pawan Kumar. And so we have, you didn't know that, okay. So we have, 2 generations, 4 Caltech individuals. So Caltech is certainly very much in the family. Okay, so now on the scientific side, I'm aiming here mainly for the non-specialist audience. So my goal is to try to convey some of the ideas that we're exploring in correlated electron phenomena in solid state, and give a little bit of a historical perspective on where these ideas are coming from, and kind of where we are right now in the context of topological insulators. I'm sure that most of you have heard of these before, maybe even have a pretty good idea what they are. So I'll give you my take on it, with an emphasis at the end on fractionalized. So this is going to connect a little bit with Jason's talk this morning. So the common element there being the fractional quantum Hall effect and how the degrees of freedom of an electron can split apart in some way. And there turns out to be many possibilities. So I'd like to acknowledge my collaborators on this project. So Mehdi has been quite a strong postdoc with me. He's now left, but he did some work on some of the systems that I'll talk about. Victor is a former student of mine. He's now a postdoc at Urbana-Champaign. And Joseph Macieko was never an affiliate of my group, but we're collaborators. He's currently at the University of Alberta. He's an assistant professor there, but he's also quite a leader in this general area of fractionalized topological phases. So here's an outline of the talk. I'm first going to give you a brief history of exotic phenomena in condensed matter physics. So I view fractionalization of the electron as a kind of exotic phenomena. So I'll give a little bit of the historical precedent. What do we have in experiment in particular, as well as what are some of the key ideas that have been around. I'll review topological insulators, just to make sure that we all have the fundamentals. And then I'll talk about some of the work that we've done in fractional topological insulators, and then wrap up with some of the open questions and current research directions in the field. Okay, so for orientation, condensed matter physicists are usually obsessed with phases of matter and different types of order in these systems. So typically we're interested in large numbers of particles. Often it's Avogadro's number, but in nearly all cases it's more than 10 to the 18 particles. So we're generally close to the thermodynamic limit. So if we're in equilibrium, then we have a well-defined notion of phases and phase transitions. And so we try to leverage that to the extent possible. And so once we have some idea of a phase, we need a way to distinguish phases. And so there have been many efforts over the years in condensed matter physics to classify phases of matter. How do we say that one type of solid is different than another type of solid, for example? So we all know solid, liquids, and gases. In condensed matter, we're usually interested in solids, and we want to know what's the difference between one solid and another solid. So a simple classification would be how well they conduct electricity. So something like copper conducts electricity very well, so we call it a conductor, or a metal. Something like silicon does not conduct electricity well if it's undoped. So that's a semiconductor, or technically it's an insulator. And so that's a first classification. But then on top of that, we might ask, well, does it have any kind of magnetic order? So you could take any metal or any insulator and ask, well, does it have a magnetic order? So you might have a ferromagnetic type of order. So we could say, well, what are the types of orders that it could have? It could be a ferromagnet, it could be an antiferromagnet, it could have some kind of unusual spiral magnetic order, and so on. So we can also ask about the structure of the crystal itself and classify systems based on their crystalline symmetries, as well as their ability to conduct or not conduct electricity, as well as their ability to have different types of magnetic configurations and local moments in the system. So we can keep making a finer and finer and finer classification of these solid state systems. But what's been realized in the last 2 decades or so is that the original ideas of classifying things, which were based on properties that were very local in space, that we could measure in principle locally, such as the charge density around an ion, or the magnetic field around atoms or around the surface or the bulk of the sample. Those are all things that have a well-defined, measurable quantity that's local in space. But there are other aspects to solids that you can't probe locally. You somehow need a global information about the system. And so these are various types of topological orders. Okay? So they're a little bit more subtle because you can't take a particular experiment in most cases and probe something that will tell you that system is topological. Now, it turns out that in certain systems, if you know the mapping between the topology and certain observables, then with a high degree of confidence, you can do things which are essentially local and still measure them. So surface states of topological insulators are what I'm alluding to there. So in the good old days of solid-state physics, we would study crystalline solids by calculating the electronic band structure. So for those who haven't had a course in solid-state physics, or it was so long ago that you forgot, the main result of having this discrete translational symmetry of a crystal is that the momentum of the electrons are no longer precisely defined. They're only defined up to some quasi-momentum, some reciprocal lattice vector. So as a result, the dispersions of the electrons, how the energies are related to their wave vector, becomes periodic in momentum. And so one plots these dispersions along certain directions in space, and because of unusual crystal symmetries, those dispersions typically are different in different directions. And so if we make this kind of a calculation, which we can now do with actually a very high degree of accuracy using something called density functional theory, then we know how the energy of electron is related to its momentum as it moves through the crystal. And so for a material like silicon, for which this is the electronic band structure, this tells us a lot about how the material would respond to electric fields, for example. Or if you shine light on the system and you excite electrons out of their ground state and create a kind of hole in a particle-like excitation, we know how much energy that would cost, what the wave vectors and energy momentum conservation rules would require. As well as, we can see that there is a gap in the excitation spectrum. The energy 0 here is the Fermi energy, which is the most important energy in solid-state systems. And here, the system is very close to being an insulator, and there are these little blue electron, conduction pockets. So if we had this band structure, say, in the 1950s, we would say that we know quite a lot about that material. We know how these electrons disperse. So this picture of this electronic band structure essentially underpins most of modern electronics and communication devices, such as the transistor. So your iPhone and a lot of those technologies are based on materials that we, for the most part, understand in terms of this kind of picture. But we now know that this is actually not generic, that you can write down a picture with these kind of dispersions, because the underlying assumption in this kind of picture is that the fundamental excitations in the system are electron-like. And we know now that that's not true. So Jason, earlier this morning, gave a great example of the fractional quantum Hall effect and these non-abelian anyons as excitations which are by no means electron-like. So we can only go so far with this, and generically this picture breaks down when the correlations between the electrons become stronger. Now you might wonder, if you're not a solid-state physicist, how can some material have strong correlations and another material have weak correlations? I mean, it's just all electrons, right? Electrons going around the nuclei of atoms. Well, it turns out that the importance of the correlations is essentially related to the relative strength of the potential energy to the kinetic energy. So these kind of electronic bands, which are derived essentially from how electron orbitals overlap each other on different atoms, if those overlaps are very small, there'll be very small movement of the electron through the crystal, so the kinetic energy can be rather small. The potential energy is essentially what it is, given by the Coulomb interaction. And so if the kinetic energy is small, Coulomb energy is what it may be, then you can end up in a regime where the Coulomb energy is very large compared to the kinetic energy, and it's that ratio which really determines whether or not your fundamental excitations are going to be electron-like or something more exotic. So if the potential energy is large, then we have the potential to have something which is not electron-like at the excitations. So that's really a lot of what's at the heart of modern research in condensed matter physics, both in the experimental side and the theoretical side. So I want to give a couple examples now where electron correlations are very important. So the fractional quantum Hall effect was already mentioned this morning. Here, what's important for us is that it's an example of non-local topological order as well as fractionalization. So just to remind you of what this effect is, typically you have some kind of a semiconductor which is doped and placed right on top of some other semiconductor which may be doped or undoped, but it's in some way different, so that the interface of these two semiconductors, each of which is thought to be relatively weakly correlated and describable by the band structure that I just showed you, this two-dimensional electron gas is placed in a perpendicular magnetic field. So this little schematic thing here is supposed to be a device which is connected to one of these two-dimensional electron gases formed at the interface of these semiconductors. A magnetic field is applied perpendicular to that system, and the magnetic field makes all the difference in the world. Essentially, it can quench the kinetic energy so that whatever potential energy is there can become a dominant energy scale in the problem and really drive you towards exotic physics. So in this experiment, you have this two-dimensional electron gas, you apply the perpendicular magnetic field, you're interested in measuring a voltage transverse, Vy here, to a current that's driven in the x direction, Ix. So the ratio of this voltage to this current gives you a transverse resistance, or a Hall resistance. And this Hall resistance will exhibit a series of plateaus at low temperature in these sort of systems. And if you look at the inverse of that, the Hall conductance, then it turns out to be quantized in units of E²/h, sometimes fractionally quantized. When it's fractionally quantized, that's the fractional quantum Hall effect. And when it's an integer, that's the integer quantum Hall effect. And so this is the sort of data that one typically gets. So if the resistance is quantized, it's a plateau, the conductance will be. So you see various regions here. This number 1, that is the integer quantum Hall effect with 1 unit of E²/h. There are other plateaus that you can see quite clearly. What's shown here is the longitudinal resistance Rxx. That's the resistance in the direction of this driving current. And if you look carefully, you can see whenever there's a plateau in the transverse resistance, there is a 0 or a near 0 in the longitudinal resistance. So you have a dissipationless current flow whenever there is a plateau in this Hall resistance. And so this phenomena and these certain integers here tell you what is the ratio of the number of electrons to the number of flux quanta in the system. So they tell you about the fractional quantum Hall state at 1/3 filling, or et cetera. So this is an experimental phenomena which was discovered in the early 1980s, and it has a number of interesting properties that I want to emphasize here. So one, there are no broken spatial symmetries. So this is an electron gas, which is essentially some kind of an electron liquid. There's no kind of order among these electrons that you can measure locally, besides that they've broken time reversal symmetry because of this magnetic field that's present. This effect requires that there be fractional charges, requires that these electrons be interacting. So fractionalization always goes hand in hand with interacting particles. And there is something called the bulk boundary correspondence, which has come up in a number of other contexts. John Preskill mentioned this idea, this kind of holographic principle, where if you know what the physics is on the boundary, you can infer something about the physics on the interior. And the fractional quantum Hall effect is one such example of a system, which is describable by Chern-Simons theory. So here is the action of Chern-Simons theory. This piece that I've written out here is the part which contains the universal topological information. It tells you about the linear response of the system, what is the Hall conductance, as well as what kind of excitations are in the system and what are their mutual statistics. So interestingly, we heard yesterday that the Chern-Simons theory is also used in order to understand the properties of knots. So we heard the example of physics feeding into mathematics. So this Chern-Simons theory is one of the star children, if you will, of the topological phenomena in many branches of physics. And it plays a major role in even systems which are formally not fractional quantum Hall systems. So the second example is high-temperature superconductivity. So here we have correlated physics in transition metal oxides, and this class of materials is quite important. So the high-temperature superconductors are often described by this kind of generic phase diagram. So along the vertical axis here is the temperature. The horizontal axis is a doping of the system. And one of the first materials was this yttrium barium copper oxide, or YIBCO as it's often referred to. So it's a series of planes of these various atoms. You can see the coppers and the barium, yttrium, et cetera, listed there. So it's some kind of a layered structure. What is unusual here about this superconductor is the parent compound, if you will. The undoped system is an insulator. So this was quite a surprise. And when it was discovered in the mid-1980s, in fact, it was such a surprise, I think the Nobel Prize was given just a year after the announced discovery of this material, because it completely changed the understanding of superconductivity on its head. Prior to that time, we had the BCS theory of superconductivity, which is based on a metallic state which undergoes a pairing instability and then becomes a superconductor. Electrons form bosons, and those bosons condense. In this case, we didn't have these free electrons. We have an insulator. In fact, we have an insulator with magnetic order. So the phenomenology associated with this phase diagram has been quite a challenge to explain in a very consistent way. And in fact, it's one of the most open questions in solid state physics. So how do we understand this phase diagram in a way that everyone can agree on? So if you have any familiarity at all with this field, you know that there are a number of distinguished physicists that have their own ideas for how things work, and they don't always agree with each other. So highest transition temperatures, as far as I know, are still less than 200 Kelvin. They are still creeping up bit by bit, but they're not at room temperature. So a lot of the promise of high temperature superconductivity in terms of low power transferring of electricity or something like this along superconducting wires is not really feasible at this point. And I want to kind of draw a bigger message from these two examples of the fractional quantum Hall effect and the high temperature superconductivity, because these two phenomena, which are discovered in the lab first, have played really an outsized role in motivating a lot of the ideas in condensed matter physics, as concerns strongly correlated phenomena. So the fractional quantum Hall effect gave us an example of a class of fractionalized electronic states with some kind of non-local topological order. So as strange as it may sound that we could break the electron apart into units that had charge less than the electron, and as strange as it may sound to say there's some kind of a non-local topology in the system, the fractional quantum Hall effect, by virtue of the very high quality of those experimental systems, really gives us a compelling example that that type of phenomena can occur in principle. So it allows us to then dream further. Can we find that type of physics in other systems? So it has inspired many subsequent developments, including fractionalization ideas in high-temperature superconductors, as well as some of the phenomena in topological insulators. We saw yet another example this morning from Jason, which is related to ideas of topological quantum computation based upon non-abelian anyons, whose ideas are strongly tied to the fractional quantum Hall effect. So, this system has had a very strong influence on the kind of ideas as well as the subsequent development of various fields in condensed matter. Now, the high-temperature superconductors, because of their unusual insulating correlated parent state, have inspired a number of novel ideas in quantum magnetism. Notably, the quantum spin liquids have received a lot of motivation and push from the study of high-temperature superconductors. There are compelling proposals that if you dope a quantum spin liquid, you end up with superconductivity very naturally, with spin fluctuations mediating the pairing between those doped carriers. And so, the study of quantum spin liquids, which, by the way, I guess I should define them, these are systems that have local magnetic moments but don't order at 0 temperature. So if you have a generic system that has some kind of a local magnetic moment and you take it down to 0 temperature, it will have some kind of magnetic order, ferromagnetic, antiferromagnetic, something. It's quite unusual that the system does not order at all. And so usually that requires some kind of frustration, and quantum fluctuations really need to be an important part of the physics. And this study of spin liquids, of course, connects also to the work of Kitaev. So he wrote down, I guess it was about 15 years ago, I've lost track of the exact date, a very important model which could be solved exactly to show that a local moment model could support this quantum spin liquid state. Prior to that, there were only approximate methods that solved these systems. So skeptics would always wonder, well, is it really true that a system in principle at 0 temperature could have no magnetic order? But we now know, because of Kitaev's work and various generalizations that have followed from that indeed, this is possible. So, this is an active area of research in quantum magnetism. Quantum criticality, so this is a 0 temperature phase transition as a function of some parameter in the Hamiltonian. These ideas are integrally related to the study of high temperature superconductivity, and is still quite an active area of research. So many theoretical ideas have been inspired by trying to understand this challenge in high temperature superconductivity, and also on the more practical side, materials are always an issue in any condensed matter solid state system, so these have helped push the fabrication technology in material science more generally, so that we have better materials for whatever kind of phenomena we're interested in, not just high temperature superconductors. Okay, so these ideas here I'll come back to at the end of the talk because they'll actually feed into the fractionalized topological insulators. Okay, so the new kid on the block in solid-state physics are these so-called topological insulators, and these are a few of the standard examples: bismuth-2, selenium-3, bismuth telluride, thallium bismuth selenide, and combination of tellurium and silurium. These materials are kind of the workhorse topological insulators. The way they are identified experimentally is through photoemission. You send in a photon and you eject an electron, and you look for the dispersion of the surface states. So it turns out that the surface states are the easiest way to probe that a system is a topological insulator. And what you see in the clearest examples are this kind of Dirac-like dispersion. So it's a linear dispersion. You have one of these Dirac cones in the surface state boron zone, this region of restricted momentum space. And this is highly unusual. In fact, it's strictly forbidden if the system is not a topological insulator, because there's a theorem that says that these Dirac cones always need to come in pairs. On a topological insulator, you can evade the theorem by having one partner on the surface that's above, another one on a surface below, say in a kind of cube geometry. So if you see a single Dirac cone in the boron zone, that's a smoking gun signature that that system is a topological insulator. So this is photoemission data. These are calculations based on density functional theory, and you get qualitative or even quantitative agreement with these systems. And so these Dirac cones can be exposed in the gap of the system as it is here, or they can be kind of buried. And depending on what you're interested in, you may be quite keen on having a particular situation or the other. So I should also mention that these topological insulators are driven by spin-orbit coupling. So that's really the crucial ingredient. You take a boring insulator, if you will, and if the spin-orbit coupling is strong enough, which is kind of the incarnation of special relativity, if you will, in the solid state, then you can rearrange the electronic band structure in order to create a topological transition between something which is boring and something which is a topological insulator. So the spin-orbit coupling locks the momentum to the spin, and so in this picture here, this Dirac cone, if you're moving in a certain direction, you have a particular spin orientation, and if you're moving in the opposite direction, you have the opposite spin orientation. So there's a very strong locking between the spin degree of freedom and the momentum degree of freedom, shown also here in this cartoon. And so this particular feature is quite appealing from the point of view of spintronics, where you want to use electric fields to manipulate the magnetic degrees of freedom of particles in a solid. So, as is widely appreciated, Moore's law is likely to end, our doubling of the density of integrated circuits relatively soon. So we really need to worry about quantum effects, and so we can either go to quantum electronics, or we can start using something other than the electronic charge in the basic computing elements in electronic circuits. And so one idea that's floating around out there, it's been there for at least 15 years now, is to use the spin. So topological insulators nicely connect into this field of spintronics. I should mention here the Caltech connection. The first experimental observation of a 3D topological insulator was done by David Tsai, who is on your faculty and doing very good work. Okay, so what can you do with the topological insulator? I mentioned spintronics. Let me just give you one more unusual thing. The surface of a topological insulator is essentially a quantum Hall state in disguise. So if you apply a magnetic field in the right direction, then you reveal the surface of the topological insulator as a quantum Hall state. And as a result, you have some unusual phenomena that are integrally related to that quantum Hall system on the surface. So if you have a topological insulator with some kind of magnetic order, you can create some kind of an optical modulator where light would pass through it in the absence of an externally applied magnetic field. If you apply an external magnetic field, nearly all the light is reflected, so you could have a very fast switch that controls the light. If you apply a perpendicular magnetic field, the light that is reflected will have a very large angle of rotation of its polarization if you started with linearly polarized light. So there is a giant Kerr rotation that is close to 90 degrees, which is far bigger than any other known system. So for applications that involve very large rotations of the polarization of light, these kind of materials may also find application. Okay, so now I want to move towards the main topic of the talk with that background. So moving towards fractionalized topological insulators. So the key idea can be summarized in this phase diagram here, which I refer to as the Pessin and balance phase diagram. So we already had the Fisher phase diagram earlier from Santa Barbara. Here we had the Pessin and balance phase diagram from Santa Barbara. And so here it is on the left. So on the vertical axis is the ratio of the electron interactions to its kinetic energy. This is the same ratio that I mentioned earlier that's crucial for determining the correlations in the system. So along this axis, if U is small, you're close to the origin, you either have a metal or a band insulator of the type that I showed earlier. If U is sufficiently big, you have something called a mod insulator, which is an insulator that's driven by the intrinsic interactions of the electrons. So this is the axis along which high-temperature superconductors lie. Typically, they're going to be around here somewhere, very close to the Mott regime. The horizontal axis here, this is lambda, this is the strength of the spin-orbit coupling relative to the characteristic kinetic energy in the system, T. This axis, when you're far out to the right, this is the regime of strong spin-orbit coupling. This is the regime of the topological band insulators. And so topological insulators here, say high-temperature superconductors here. What has not been explored much in the history of condensed matter physics is the regime where these two are significant. So the regime out here, where you have strong correlations and strong spin-orbit coupling. So there's the basic question of what kind of new phenomena might you find out there. So, an example of such a new phenomena is a topological Mott insulator, which was predicted in this paper from Dima, Pessin, and Balance. And this is a phase diagram that was calculated within a particular model over here. And in a nutshell, if you start at strong spin-orbit coupling, you'll be in a TBI, topological band insulator. And if you crank up the electron interactions U, you'll reach a point where the electron-like character of the excitation breaks down, and you're left with something else, a topological Mott insulator. So just like over here, you get Mott physics if the correlations are too big. The excitations are not electron-like. Over here, the excitations are not electron-like, yet the material is topological. So in this particular example, the spin excitations have a topological character, but the charge is uninteresting. So what we have done over the past few years is to really decorate this phase diagram with a number of different phases. Okay, so there's this TCI star, TI star, TCMI, and TCI. So in the remaining time, I'm basically going to give you a quick overview of what those phases are and how do we find these new phases. So before we go into interactions, I want to mention one more feature of the topology. These topological insulators of the bismuth selenide type that I mentioned earlier require time reversal symmetry as well as strong spin-orbit coupling. Those are the crucial ingredients. If you break the time reversal symmetry by applying a magnetic field, then the system can't have a topological property in the strict sense. So time reversal symmetry is an essential ingredient. Now, it has since been realized that the symmetry of the crystal itself can also give rise to topological invariance. In particular, there's something called a mirror churn number. So certain crystals will have planes of mirror symmetry. And so along these planes in a three-dimensional system, you basically have a two-dimensional system, and you can calculate two-dimensional like properties, like the churn number for the integer quantum Hall effect. And it turns out that if you have such a non-trivial churn number related to the mirror symmetry, then certain surface properties follow. So you have excitations that are in the surface that are located at particular points in momentum space, a lot like the topological insulators that I showed you earlier. So one thing that we did was we asked whether or not this type of topological crystalline insulator, topology from the crystal symmetry, can occur in these transition metal oxides, the same rough class of materials as the high-temperature superconductors. And we found that they could in principle. So we returned to this Pessin and balance calculation. In fact, we used the same Hamiltonian, and we showed that this topological band insulator phase that they found was doubly topological, at least. So not only was it a Z2 time reversal invariant topological insulator, but it was also a topological crystalline insulator. So this emphasizes the point that in the classification scheme of various materials, we need to ask many questions about what kind of topological invariants they are. So we need to identify all possible topological invariants and then ask a yes or no for each of them. So a system is not topological or not, but it's topological in a particular way or not. And so in principle, we need to know what are all possible ways they can be topological and then answer that question, because each way of being topological has specific implications for the observable properties. Now, since this is a talk that's focused on correlation effects, we asked what happens to these topological crystalline insulators, topology from the crystalline symmetry, if you crank up the interactions. And essentially what you find is that you, again, make a transition into some kind of a strongly correlated state, which we call the topological crystalline Mott insulator. So it's a Mott insulator because the excitations are not electron-like. It's topological because the spin excitations have a topological structure that follows from the crystalline symmetry. So the way that you study such systems, well, one way to do it is to take the electron operator, which here is D. This is an annihilation operator for an electron on site J with spin projection gamma. You write it as a product of two pieces, one piece which carries the charge of the electron, one piece which carries the spin of the electron, and this allows the system, the electrons, to split apart into charge pieces and spin pieces. And so this kind of a decomposition allows you to gain access to those types of phases. Now, another cousin of this is this Ti star. And so the decomposition that I showed you, the electron into charge and spin pieces, is a very natural one in some ways, but it's not unique. We can take this electron operator here at C, sorry for the change in notation, and split it up into a product of some kind of a pseudo-fermion and a pseudospin. So in this case, this pseudo-fermion F contains both the original charge and the original spin of the electron, but also some additional degrees of freedom, which are properly described by this pseudospin. And so if we substitute this into an interacting Hamiltonian, then we get some other kind of possibilities. Namely, we can get states that have loop-like excitations and particle-like excitations. And there's some details here, and I'm running out of time. So I'll just say quickly that this is described by something called a BF theory. And so there's a 2-form here, B, which describes the loop. There's a 1-form, A, here, which describes this particle. And they have a non-trivial mutual statistics. And because this F operator that I mentioned contains both the spin and the charge degrees of freedom, it has the same kind of electromagnetic response as a conventional topological insulator, but in addition it has a ground state degeneracy, which is topological. So it's like a Z2 quantum spin liquid plus a topological insulator for the experts. So the same result is borne out at the mean field level, and we can calculate actually that statistical angle of pi directly. And we find that the mean field results actually reproduce the field theory result that I showed you. So, so that was quick, but I showed you essentially how we could get these topological crystalline Mott insulators, the Ti star phase, which is the decomposition into F and pseudospin. You can also have a topological crystalline insulator star, which is the same formalism that I just showed you with the F and the tau, but taking into account the crystalline symmetry. And there are many, many more possibilities that, in principle, one can dream up. And here's a table that kind of summarizes the overall picture. This will appear in a Nature Physics Progress article soon. So the idea here is actually very similar to the high-temperature cuprate superconductors. You have a parent state, which is some kind of a non-interacting topological state, and then you add interactions into the system, and you get some kind of fractionalized state. And so depending on how the electron splits apart into different degrees of freedom, you get different classes of fractionalized states. Okay, and so here's a pictorial representation of these. So in the interest of time and keeping us on schedule, I won't dwell on those. I'll just mention this last one here, where the charge of the electron can split apart in this 3D topological insulator, very much like the charge of the electron can split apart in the fractional quantum Hall effect. So there's this possibility as well. Okay, so to summarize and conclude, what we've done is present interacting lattice models that can realize fractional topological phases. I focused on these transition metal oxides. They're a promising venue for these topological phases that are interacting because they have the right ingredients. You can put heavy transition metals in there, which gives you a large spin-orbit coupling effect. The d orbitals of those transition elements gives you flat bands and therefore strong correlation effects. So you can combine the strong spin-orbit coupling and the strong correlation to potentially bring out new phenomena in these systems. What is currently a very active area of research, and in fact quite an ambitious one, is to classify these possible phases for all of these interacting topological systems. And so that's where we are right now. So thanks very much for your attention.